Every time you stream a video or send an email or even just search for something online, you're tapping into this massive global network of computers. But behind that whole seamless digital world, there's a hidden cost, and it's a huge one: energy. We're about to pull back the curtain on the quiet energy crisis that's powering our digital lives and the brilliant folks who are racing to solve it.
So, for as long as we've had silicon chips, the main goal has always seemed to be make them faster, make them smaller. But right alongside that, there's been this other, equally important war being waged against power consumption. This is the world of what engineers call power-aware computing, and it's just this constant struggle to do more with way less energy.
And believe me, this isn't just some abstract engineering problem. You feel the consequences of this war every single day. Ever stop and wonder why your phone gets kind of warm in your pocket? Or how your laptop battery just seems to melt away, even when the screen is off and it's just sitting there? Well, the answer to all of that comes down to the very nature of how a computer chip actually uses electricity.
Okay, to really get this, we've got to pop the hood on a computer chip. As it turns out, there are two totally different ways a chip sips on electricity, and for decades, engineers have been tearing their hair out over both of them.
Think of it like this, okay? Dynamic power is the energy you need to actually flip a light switch on and off. It's the cost of doing work, of making something happen. Static power, well, that's a whole different beast. It's like having a leaky faucet. It's this constant, slow drip of energy that leaks out of a transistor even when it's supposed to be completely, totally off.
For the longest time, the only thing anyone really cared about was that dynamic power. I mean, think back to those chunky computers from the 90s, right? The big monitors, the fans whirring away. Back then, pretty much all the focus was on making that flip of the switch as efficient as humanly possible, cutting down the energy it took to do an actual calculation.
And that leaky faucet of static power? Well, back then, it was just a tiny, insignificant little drip. I mean, it was so small, it was barely even a footnote in the whole power equation. The industry had a clear enemy, and that enemy was the power used for active switching. But oh boy, that was all about to change in a really big way.
So, as we cruise into the early 2000s, Moore's Law is just on fire, right? We're getting smaller, faster chips at this mind-boggling pace. But the very thing that was making everything so successful was about to create a brand new crisis, one that almost nobody saw coming.
Now check out this quote. This was a massive warning shot. Back in 2002, Intel's chairman, the legendary Andrew Grove, basically stood up and told the entire industry that the game had changed. He said the new villain, the biggest problem we were all facing, was that tiny little drip, what he called off-state current leakage. And this chart shows you exactly why he was so worried. These projections from the industry itself show this absolutely terrifying trend. While dynamic power, the energy to flip the switch, was going down, which is good, the static leakage power, that drip, was shooting up exponentially. It was a collision course that was threatening to bring all the progress of Moore's Law to a dead stop. You see, the physics here is pretty simple. The smaller and smaller you make a transistor, the harder it is to turn it completely off. The gates just get leaky. So the very solution to the old problem, shrinking transistors, ended up creating this massive new one. The drip had officially become a flood. Now, this leakage problem on one tiny little chip has enormous implications when you scale it up, like to the size of a data center that powers pretty much everything we do online. And that brings us to the data center dilemma. So let me ask you this. How busy are the servers that run the internet? You'd probably guess they're either off or just pegged at 100% all the time, right? Well, the reality is actually pretty surprising. This data from thousands of real servers shows they spend most of their lives in this low to medium activity state. And why is that? Well, they have to be ready for a sudden spike in traffic, but most of the time, they just don't need all that power.
Okay, now for the really shocking part. A typical server, even when it's only 10% busy, it's basically just idling, doing almost nothing. It still burns through more than half of its maximum power. Just let that sink in for a second. 50% of its peak power draw, just to stay on and do a tiny fraction of its job. We're talking billions of dollars and just tons of carbon, all wasted, powering machines that are mostly just waiting around.
And this right here is the paradox at the heart of the whole problem. Our computers are fundamentally mismatched to the way we actually use them. They are at their absolute worst, their most inefficient, in the exact state where we force them to spend most of their time. It's a massive, systemic waste of energy.
So what's the solution? How do we fix this? Well, it's not a simple fix. It actually requires a whole new philosophy for designing computers, a completely new way of thinking about the connection between work and energy.
It's a concept called energy proportionality. And the idea is actually really simple, but it's also radical. An ideal computer should use power in direct proportion to how much work it's doing. So if it's doing very little, it should sip very little power. If it's running at full blast, then sure, it can use its max power. It's so intuitive. Use a little, pay a little.
Let's try an analogy. Today's server is like a car that burns almost as much gas sitting in stop-and-go traffic as it does flying down the highway at 80 miles an hour. It's just incredibly wasteful. The ideal energy proportional server would be like a car that just sips gas in traffic and only really guzzles it when you slam the pedal to the floor. Makes sense, right?
Now, getting to this ideal state, well, that's not easy. It means we have to fundamentally redesign not just one part of the computer, but all of them. We have to make every single component a lot smarter about how it uses power.
And here's what's really interesting. The CPUs, the brains of the operation, they've actually gotten pretty good at this. But as they've become more efficient, the other components, we're talking memory, storage, all the networking gear, they've become a much bigger piece of the power pie. They are now the big power hogs, and they are way, way behind the curve on this proportionality thing.
I mean, this table just lays it all out. That dynamic power range is basically the difference between idle power and peak power, how much a component can throttle down when it's not busy. A modern CPU, it has a range over 70%, which is fantastic. It can go from a tiny sip to a fire hose. But now look at the others. Memory is less than 50%. And disk drives and network switches? Oh man, they are shockingly bad. They're pretty much just on or off, with almost nothing in between.
So to fix all this, engineers have to build two key things into every single component. First, a wide dynamic power range, just like the one a CPU has. And second, something they call active low-power modes. Think of it like a dimmer switch for a light bulb. Instead of just being fully on or fully off, a component can run at a slower, lower power state to save energy, but without that long delay it takes to wake back up from being completely asleep.
You know, when you take a step back and look at this whole story, you can see that the fight for energy efficiency has been a story of constantly shifting battlefields. It seems like every time we solve one massive problem, a brand new one pops up to take its place.
In the 90s, the enemy was the dynamic power it took to switch transistors. Then, in the 2000s, the battle shifted to the static power from leaky transistors. And today, the new frontier, the next big challenge, is this quest for system-level energy proportionality, making the entire machine, from top to bottom, truly intelligent about how it uses every last drop of power.
Look, this isn't just some abstract engineering puzzle. Our entire modern world, from finance and science to all our entertainment, it's all built on this foundation of computation. A foundation that is getting thirstier and thirstier for energy every single year. So the final question we have to ask ourselves is this: what happens to that world if we can't solve its insatiable thirst for power?